Hello, so welcome to this course on mathematics for signal processing. And basically this course is a collection of many topics, many mathematical topics, ranging from linear algebra, random processes, Fourier analysis, and so on. And basically, the goal is to condense in one course and in a very short period of time, relatively speaking, the background that is needed now to engage in research in topics like signal processing, communications, machine learning, and so on. We don't have time to waste. I will just dive into the first topic of our course, which is the singular value decomposition. Okay, so we'll start basically the first part of the course will be the linear algebra part. When we finish it, it does not mean that it's done. Basically, we will keep referring to the results that we get here. Okay, so SVD, I assume that everyone here is familiar with Eigen Analysis. And the problem with Eigen Analysis is something that is very nice, but there are two problems. So you can do Eigen Analysis to a matrix A. It needs to be square, so you need n by n matrix. And actually, among the square matrices, not every square matrix is diagonalizable. Okay, so if a matrix is defective, which means that one of the eigenvalues has a geometric multiplicity that is strictly less than the algebraic multiplicity, then the matrix is not diagonalizable. You cannot find n linearly independent eigenvectors, and you cannot do Eigen Analysis. You can go for the Jordan canonical form. It's not bad, but also it is still for square matrices. So we want something that is very general, and this is the SVD. The trick is simple. The trick is you start with a matrix that is generally rectangular. So our matrix here is m by n. And what you do is that you obtain a square matrix by basically multiplying the matrix A by its Hermitian. Okay, so you take A Hermitian A. Okay, so if A is m by n, A Hermitian is n by n, or you basically take A Hermitian. The proof that I am providing here can be rewritten basically based on A Hermitian. Here I will do A Hermitian A. They are equivalent. So what do you gain when you write A Hermitian A? Again, your matrix becomes a square. But more importantly, this matrix is Hermitian, and it's positive semi-definite. And so it is guaranteed to be diagonalizable. Moreover, the eigenvectors of this matrix can be chosen to be orthonormal, and the eigenvalues of this matrix are real valued and non-negative. So you get very good things basically if you use A Hermitian A rather than A itself. Again, which if it's rectangular, you cannot even do Eigen Analysis. Okay, so this is the trick. The remaining part of the story is simply now, so okay, you wrote down the Eigen Analysis of A Hermitian A, which is doable, but how can you write something for A itself? Okay, so it turns out that for A itself, you will need to use two left and right matrices. So basically, if you do Eigen Decomposition for a square matrix that is diagonalizable, then you can write this as Q lambda Q inverse. Okay, so here, if you have the matrix Q, here you have its inverse, and if this matrix is Hermitian, then actually Q inverse is Q Hermitian. But now, if you play this game, actually you deal with A Hermitian A, and then you want to write down something for A itself, you will have to use two matrices U and V. And so these will emerge as we go through the derivation. Okay, so we will be able to write A as basically a unitary matrix and another unitary matrix. Okay, and between them a diagonal matrix that carries basically some non-negative real valued quantities that we will call the singular values. But the story starts with A Hermitian A. Again, because this is a square, and it is positive semi-definite, it's diagonalizable. And so what you do is that you go and do its Eigen decomposition. Okay, so you take A Hermitian A, okay, and you do its Eigen decomposition. So basically what you get is the matrix of the unitary matrix of eigenvectors. This we'll call V, we'll call this V, okay? And on the other side, you will put the inverse of V, and because V is unitary, you will have here V Hermitian. And between V and V Hermitian, you will have basically the matrix containing the eigenvalues of A Hermitian A, okay? And those, because A Hermitian A is Hermitian and it's positive semi-definite, the eigenvalues, as I said, are real valued and non-negative, okay? So I will write those eigenvalues as sigma 1 squared, sigma 2 squared, till sigma n squared. So this is something that you can do. You can imagine that those eigenvalues, because they are real valued and non-negative, you can imagine that they are the squares of some parameters, and those will basically, the sigmas themselves without the squares will be the singular values of matrix A, etc. But let's now focus on A Hermitian A. So here are the eigenvalues: sigma 1 squared, sigma 2 squared, up to sigma n squared. Of course, if matrix A has a certain rank, okay, so A Hermitian A is of size n, but the rank of the matrix may be less than n. So generally speaking, basically those sigmas will be strictly positive. Sigma 1 squared, the sigmas that are strictly positive will be sigma 1 squared, sigma 2 squared, up to sigma r squared, where r is the rank of A, which is exactly the same as the rank of A Hermitian A. Okay, so basically this thing here, there is a possibility that, some eigenvalues will be 0, so this will go to and so on. And the other ones, they are defined, but they are also equal to 0. Okay, and in this course, we will adopt basically the notation that sigma 1 is the biggest guy. Okay, so sigma 1 is the greatest one in basically in value, followed by sigma 2 and so on. So sigma 1 is greater than or equal to sigma 2, which is greater than or equal to sigma 3 and so on. And then the last strictly positive sigma is sigma r, where r is the rank of A, which is the rank of A Hermitian A. And then the remaining guys from sigma r plus 1 to sigma n, those are exactly 0. Okay. So, this is basically Eigen decomposition for A Hermitian A. Now let's try to basically manipulate this Eigen decomposition. So what we will do is that we will partition matrix V. So matrix V, again, what are basically the columns of matrix V? So the columns are the eigenvectors of A Hermitian A. And basically the columns of matrix V are orthonormal because A Hermitian A is basically a Hermitian matrix. So we will split those eigenvectors into two groups. Okay, so V sub A, so those are the eigenvectors corresponding to the strictly positive eigenvalues, and sigma B will be the remaining eigenvectors. Okay, so those are basically the eigenvectors corresponding to the 0 eigenvalue of matrix A Hermitian A. Okay, so now V can be written as VA, and so here we have our columns, okay, and then VB, and here we have n minus r columns. And then we will define matrix S. Okay, and so what is S? Is an R by R matrix. Basically, we will take the sigmas that are strictly positive, and we will arrange them on this on the diagonal of this R by R matrix. Okay, and so let's now write our basically Eigen decomposition of A Hermitian A. So here we have V again, which is now VA and VB. And on the other side, we have the inverse of V, because V is unitary. This is V Hermitian. And between them, this is the matrix. So the eigenvalues themselves are those squares. So, so here we will have this block will be S squared. And then the remaining matrix here will be all zeros. And now if you write this as VA VB, and this as VA Hermitian VB Hermitian, and then you multiply. Basically, you will get VA S squared VA Hermitian. Okay, because the VBs will disappear because they will be multiplied by all zero matrices, submatrices. Okay, so VA S squared VA Hermitian. So this is again by focusing on the non-zero part in this diagonal matrix. Okay, now, okay, so let's write this. Let's go it. So A Hermitian A is VA S squared VA Hermitian. Okay, multiply by VA Hermitian from the left. So VA Hermitian A, and VA Hermitian VA is what? So VA Hermitian VA will give you identity because again the columns of VA are orthonormal. So if you multiply VA Hermitian by VA, you will get identity. Okay, so this will give S squared VA Hermitian, and then multiply from the right by VA. So this is VA Hermitian A VA, and this is S squared. Then it's VA Hermitian. When you multiply by VA, again same thing, you will get identity. So this is what we have here. Then you multiply from the left by S inverse. S is an invertible matrix, right? Because it's a diagonal matrix, and the elements on the main diagonal are all basically non-zero. Okay, so it is an invertible diagonal matrix, and so we multiply S inverse from the left, and actually from the right also VA Hermitian A VA. And so you have S inverse S squared S inverse, and so this will give you identity IR by R, and so this is our first main expression here. Okay, so we can write down this expression. S inverse VA Hermitian A VA S inverse is equal to identity of size R by R. Okay, so again, so we don't forget what the terms we have. So what is VA? So VA basically is a matrix with R columns, where R is the rank of matrix A, and the columns are basically orthonormal, and those are basically the eigenvectors of A Hermitian A that correspond to the strictly positive eigenvalues. Okay, S is a diagonal matrix that contains the positive square roots of the strictly positive eigenvalues of A Hermitian A. Okay, so the eigenvalues of A Hermitian A are sigma 1 squared, sigma 2 squared, sigma 3 squared, up to sigma r squared. S itself is basically sigma 1, sigma 2, sigma 3, r to sigma r. Okay, so so basically we have this equation, so let's keep it. And then what if you take A Hermitian A and multiply it by VB? Okay, so if you take A Hermitian A multiplied by VB, okay, actually from the way we define VB, so remember when we partitioned matrix V, actually VB are the eigenvectors corresponding to the zero eigenvalue. Okay, so it's not surprising that if you have A Hermitian A VB, okay, you will get an all zero matrix. And you can see it another way, that basically if you take A Hermitian A and express it as VA S squared VA Hermitian, you will have here basically this matrix VA Hermitian VD. So what is this matrix? It's a matrix whose elements are the inner products of the columns of VA and the columns of VB. And basically those are columns from matrix V, and the columns of matrix V are orthonormal, and so basically those guys, when the inner products are all zero, and so you get here the all zero matrix. Okay, so this is equal to the all zero matrix. Now multiply here from the left by VB Hermitian. Okay, and of course the VB Hermitian by the all zero matrix will give 0. Okay. So this is actually what we get. Let's expand it. So VB, basically those are the columns in the original matrix V, columns VR plus 1, VR plus 2 up to Vn. And basically this side is the Hermitian of this side. And this is equal to the all zero matrix So basically, if you take a row here and a column in this matrix, you will get that for J from R plus 1 to N, so basically Vj is one of the columns of Vb, or it's an eigenvector of A Hermitian A that corresponds to a zero eigenvalue, then Vj Hermitian A Vj is equal to 0. Okay, so from here, and this is just the L2 norm squared. Okay, so this is the L2 norm squared of Vj, so we know from the definition of the norm that actually a vector norm is a norm if and only if several conditions are satisfied. One of them is that if the norm is equal to 0, then we are sure that we are talking about the all zero vector. So if the L2 norm, or here the L2 norm squared of V is equal to 0, it means that actually this guy is the all zero vector, and this is true for any. Again, this may be like a repetition. You can just say, those guys from the beginning, they are again corresponding to the zero eigenvalue of A Hermitian A. And again, this is true for all the columns of VB, and so AVB is equal to the all zero matrix. Okay, so these are the two main results that we have now. To recap, we start with the general matrix A. It can be rectangular. It's m by n. If it is a square, it can be actually defective. A matrix that you cannot diagonalize. However, what you do is that you form A Hermitian A. You do Eigen Decomposition to A Hermitian A. Okay, so you start from A, you take A Hermitian A, and basically you do Eigen Decomposition to this matrix. And so this will give you V, and then a diagonal matrix of eigenvalues, and then V Hermitian. And then here you put the eigenvalues. Let's call the eigenvalues. We know, because this matrix is Hermitian and positive semi-definite, we know that those guys are real-valued and non-negative. So we can write them as those guys. There are R strictly positive of them, where R is the rank of matrix A. And then we split V into VA of dimension n by R, and VB, basically dimension, VB will be dimension n by n minus R. Okay, and the results that we have till now are basically that A, VB, is equal to the all zero matrix, and also the one we have up here, which is that S inverse A S inverse VA Hermitian, A Hermitian, A VA S inverse. This is identity of size R. Okay. Okay. Any questions? Okay.
Excuse me, can you hear me?
Yeah.
Yes, just an organizational question. Could you please later provide us with the annotated JPEG files?
Yeah, I send it after the lecture. Yes, of course, yes.
Okay, thanks.
Thank you. Okay. Now we will do this. So remember from the previous slide, so we have this A VA S inverse, and then A Hermitian VA Hermitian S inverse, that this is equal to IRR, right? So basically this is something, and it's here multiplied by its Hermitian, right? So let's give this thing a name. Okay, so this will be UA. We can do this. Okay, nothing will AVAS inverse, and this is its Hermitian. So we will basically call this UA, and so automatically this thing will be UA Hermitian. Okay, and so UA Hermitian, UA is equal IR by R, and UA is of size M by R. So basically this matrix UA, since UA Hermitian UA is equal to IR by R, then the columns of UA are also normal. Okay, and so basically the inner product of a column with itself is 1, and with another column is basically equal to 0. Okay, so here is where matrix U will enter into the picture, and it is related to matrix V. So basically UA is AVA S to the minus 1. Okay, now we will complete basically the columns of matrix UA to obtain a square matrix that is unitary. Okay, so UA, again from the dimensions, this is M by N, VA is N by R, S inverse is R by R, so UA is M by R. Okay, so those are R columns, and don't forget what is R. R is the rank of A, which is the rank of A Hermitian A. Can we just complete, basically, so this is basically R vectors living in the M-dimensional space. So let's complete the M-dimensional space by constructing matrix UB, okay, such that if you take UA and append UB to it, so that now this thing here, so this is M by R, this is M by M minus R, together they will have M columns, okay, and it will be a unitary matrix, okay. So now U is M by M by M, okay. And conceptually, I'm not saying that this is how it's you obtain this thing like in professional software for linear algebra, but conceptually, how can you if you have like some vectors and suppose, let me give an example, okay, rather than just talking. So suppose that you have like let's do like a tiny example. M is equal to 3. So suppose that you have a vector like this and another vector like this. So those are two orthonormal vectors, but they live. There are two of them living in the three-dimensional space, right? So suppose that you want three vectors. You want three vectors. Can you do this? So because like you may look at this step and say, well, how do we know that we can actually obtain matrix U sub B? What you can do is that you can take these two columns. Okay, so here it's like M is equal to 3 and R is equal to 2. No, of course, I didn't mention it explicitly, but perhaps I should, that R is the rank of matrix A, right? R is rank of A, okay, and A is of size M by N. So by definition, the rank of matrix A will be less than or equal to the minimum of M and N, right? So R is always less than or equal to M. Okay, so we have basically those M-dimensional vectors, and we have R of them, and we wish basically to have M of them. One way of doing things is basically to append the identity. Okay, if I remember correctly, what is going on, and then you can apply Gram-Schmidt. Orthogonalization. Okay, which you have learned in some previous linear algebra course or in some other course. Okay, and so basically what you do is that, so you have these two guys, they are orthonormal. Then you go to the third guy, and what you do is that you take the vector itself. Okay, and so you do Gram-Schmidt, and so what you do is that you subtract this first vector. Okay. Multiplied here by the inner product of these two guys. So what is the inner product? It's 1 over square root 2 times 1 plus 0 times 0 plus 1 over square root 2 times 0. So this will be 1 over square root 2, right? And then you have the second column, which is 0, 1, 0. Okay, and you multiply by the inner product. So between these two guys, so 0 times 1 is 0, 1 times 0, 0, 0, 0. So basically this is 0. Okay. So you basically take a vector here, a column here, and you subtract it from a linear combination of the previous columns, okay, and the weights of the linear combination are basically the inner products. And so what is this thing here? So this is 1 minus 1 half, and so 1 minus 1 half is like 1 half, okay, and 0 minus, so this is 0, and 0 minus 1 half, so that's minus 1 half. Okay, so you obtain a vector like this, and then you basically divide it by its L2 norm so that it's normalized. So, okay, so that's the third vector you are after. So basically, your vectors now becomes 1 over square root 2, 0, 1 over square root 2, 0, 1, 0, and that, how to complete the space is by 1 over square root 2, 0, minus 1 over square root 2, and you can check that basically this is a unitary matrix. suppose that in another example, that the first column of identity is actually a linear combination of the vectors that you already have. Then conceptually, when you do this operation, you take this vector minus the combination of the others based on the inner product, you get a 0. So if you get a 0, you will skip this one and try with this one. Okay, and if you get a 0, you skip it and go to the third one, and so on. Okay, my point here is that you can do this. This is doable. Okay, you can start with R, basically orthonormal vectors, and then living in the m-dimensional space, and you can end up with a full unitary matrix. So m-dimensional vectors. Okay. Now, because of course this matrix is unitary, by definition it means that its columns, the inner product of any vector in UA and UB will give you 0. Okay, so so basically this is what is here. It means that these new vectors by design in UB you actually obtain them such that they are basically orthogonal to everything in UA. So this is matrix U. So it comes from this guy here. Now we are close to basically finishing the argument. Now let's examine U Hermitian AV. Okay, U Hermitian AV. So again, the idea here is that we want to say something about matrix A itself. Our starting point was A Hermitian A, but now I want something basically that can be used for matrix A itself. So let's examine U Hermitian AV. So U Hermitian is UA Hermitian, UB Hermitian, okay, and AV is basically AVA and AVB. Now do the multiplication, so basically this will be UA Hermitian AVA, and then UA Hermitian AVB. Remember that AVB will give you 0, and then you have UB Hermitian AVA, so that's it. And then because AVB is equal to 0, then you get here also a block of zeros. Okay. Now, look here, basically, how do we define UA? So here, UA is AVA S inverse, okay? So what if you multiply both sides by S? Okay, so UAS is equal to AVA, okay? UAS is equal to AVA, and so you use it here and there. Okay, you use it here and there. And what is UA Hermitian UA? Well, UA Hermitian UA, those guys are basically orthonormal, and so here you get identity of size R, and here you get UB Hermitian UA, and basically the columns of UB by design are obtained to be, are obtained in such a way that they are orthogonal to every column in UA, and so this will give you an all zero matrix. Okay, so basically UA Hermitian AV will be this very nice matrix. U Hermitian AV will be a matrix that is basically all zeros, okay, all zeros, but then it has here a block, an R by R block that contains those parameters we called sigma 1, sigma 2, up to sigma R. So those are basically the square roots, the positive square roots of the eigenvalues of A Hermitian A. Okay. Now, matrix U is unitary, matrix V is unitary, so you can basically take this. So let's call this matrix sigma. You can multiply from the left by U, you can multiply from the right by V Hermitian, and you get this thing. A is equal to U sigma V Hermitian, so A is M by N. U is a unitary matrix M by M. Sigma is this matrix which is M by N, and again it's an all zero matrix, except that the other, the upper left corner is you have this R by R basically invertible matrix containing the positive parameters sigma 1 up to sigma R, and then V itself is N by N. Okay, so this is this is called the full SVD, the full singular value decomposition of matrix A. And if you basically multiply, so if you split U into UA, UB, V into VA, VB, and do the multiplication, you can write A as basically UA S VA Hermitian. So UA is M by R, and S is R by R, and VA Hermitian is R by N. This is called the reduced SVD. Okay, so any restriction on matrix A? No, no. Okay, so the trick was basically the bridge to write down something for a general matrix A was to basically do this A Hermitian A trick, which allows you to have basically a Hermitian positive semi-definite matrix that you can diagonalize using orthonormal eigen vectors. And now those sigmas, together with sigma r plus 1 up to sigma the minimum of m and n, those are called the singular values of A. So the singular values of A, those are the sigmas. Remember when we did the eigen decomposition, the sigma square were the eigen values of A Hermitian A. So the singular values of A are basically a square root of eigen values of A Hermitian A or A Hermitian. Okay, so you can repeat everything playing the game with A Hermitian. Now the columns of V are called the right singular vectors. Okay, and the columns of U will be the left singular vectors. Okay, so it's no longer like singular vectors, because like in Eigen Analysis, we have like, you know, the matrix, and on the other side we have the inverse of the matrix. But now we have actually two matrices, so we call the matrix V. So basically this is the matrix of the right singular vectors, and the matrix U is the matrix of the left singular vectors. Okay, and you can show that basically if you take A Hermitian, you get US square, and you know those zeros multiplied by U Hermitian. Okay, so this is basically the SVD. And again, you can write it with basically the full unitary matrices U and V, or you can basically trim it and have here a diagonal square matrix, which is S. Now, during the proof, we basically showed that AVB is equal to the all-zero matrix. Okay. So what does this mean? I mean, so if you have a matrix multiplied with matrix A multiplied by a bunch of columns living in matrix VB, and this is basically the all-zero matrix, what does it mean? It means that A multiplied by any column in VB is 0. So basically the columns of VB are living in the null space of matrix A. So if you see an equation like this, you are sure that basically the range, the column space of VB is a subset of the null space of NA. Okay. Now, what is the dimensionality of basically the range of VB and the null space of A? Okay. So recall that VB is a matrix that is of size n. By n minus r. Remember that we have matrix V, we split it into VA and VB. So those are our columns corresponding to the strictly positive eigenvalues of A Hermitian A, and those are the remaining eigenvectors corresponding to the 0 eigenvalue. And so those are orthonormal, so they are linearly independent, and we have how many of them? We have n minus r of them. So basically, the dimensionality of the range or column space of VB is equal to n minus r. Okay. What about the null space of A? What is the dimension of the null space of A? So we can use the rank nullity theorem. So the rank nullity theorem tells you that, okay, so rank nullity, it tells you that the rank of A plus the dimension of the null space of A, this is equal to the number of columns of A, which is n, because A is m by n. Okay, so what is the rank of A? So the rank of A is r, and so what is the dimension of the null space of A? So it is n minus r. So basically, because AVB is equal to the all-zero matrix, this means that the column space of VB is a subset of the null space of A. But guess what? They have the same dimensionality. The dimensionality of the column space of VB is n minus r, because basically VB is, it has n minus r orthonormal columns, and the dimensionality of n of A is n minus r, where r is the rank of matrix A by the rank nullity theorem. And so basically these two guys, they have the exact same dimensionality. So basically, actually, this, so it's RVB is actually n of A. Okay, so we have this equality here. So let me remind you, this may be like something that you learned in a previous life. It's nice basically to have this refresher. How do we prove that two sets are equal? Okay, so suppose that you have two sets. Okay, and one of them, let's say psi, and the other is omega, and it is required that you show that psi is equal to omega, right? Of course there are, I don't think there are just two tricks, but I will mention just two tricks. So first, basically, idea is that you show that psi is a subset of big omega, and then you show that big omega is a subset of psi. Okay, and then, so if psi is a subset of big omega and big omega is a subset of psi, then they are the same. Okay, so this is, very useful, and, I think we'll encounter this again and again and again. So you want to show that two sets are equal. These two sets here are basically those, the column space of VB and the null space of A. Well, again, you can show that one is a subset, each one is a subset of another, and so basically you have two basically sub-proofs, and you finish them, and then, yeah, so you have equality. So the second idea is, you show that psi is a subset of omega. Okay, so basically this tells you that the dimension of psi is less than or equal to the dimension of omega. So if you continue, if you show that the dimension of psi is exactly equal to the dimension of omega, you are done. Okay, so you show that psi is a subset of omega, but actually they have the same dimension. So again, the conclusion will be that the two guys are the same. Okay, so basically I'm using this second idea here. I argued that this is a subset of that, and then I said, well, let's examine the dimension. So here the dimension is n minus r, here it's n minus r, then actually these two guys are the same. And so the columns of VB are actually an orthonormal basis for the null space of A. So if you have a matrix A, and you are interested in obtaining basically a basis for its null space, then what you are hunting for are basically the columns of VB. Those are an orthonormal basis for the null space of A. Okay, so those those matrices, so those singular vectors, they are like, they're not just singular vectors, they are playing a very important role, right? So here again you see that the range of VB is equal to the null space of A. Now what about the U matrix? Suppose that X is in the range of A. So it means that X is in the column space of A. It means that there is some vector Y such that if you multiply A by Y, you get X. That's the meaning of the X being in the range of A. It means that it can be written as a linear combination of the columns of A. Okay, but what is A? If you write down A using the reduced SVD, then A is equal to UA SVA Hermitian U. So basically, X itself can be written in this form. It can be written as UA multiplied by a vector is equal to X. So it means that X also is in the column space of UA. So what is this line? It tells you if you start with a vector in the column space of A, this vector is guaranteed to be in the column space of U sub A. Okay, and so basically the column space of A, or the range of A, is a subset of the range of UA, right? Because again, you start with any vector here, it must end up there. So R of A is a subset of R of UA. But what about the dimensionality? The dimensionality of R of A, well, the dimension of the range is the rank, and the rank is R. What about the dimension of R of UA? basically UA is an M by R matrix. So it has R columns that are orthonormal, so they are linearly independent. And basically the dimension of the column space of U sub A is R also. So basically these two guys, you know, so RA is a subset of RUA, but they have actually the same dimensionality. So actually they are the same, they are equal, okay? And so the columns of UA are an orthonormal basis for the range of A. So you have matrix V, which is equal to VA, VB, and you have matrix U, which is equal to UA, UB. And now we have those very nice conclusions that basically VB, so this is an orthonormal basis for the null space of A, and UA is basically an orthonormal basis for the column space or the range of A. Okay, any questions? Okay. Again, this is A, and this is the reduced SVD. So this is the reduced SVD. And now, so basically, UA will be R columns that are orthonormal, and VA will be basically the R columns that are also orthonormal. And here we have S, which is an invertible diagonal matrix, and those are the singular values. Remember that sigma 1 is greater than or equal to sigma 2, greater than or equal to sigma R, which is strictly positive, and then the remaining singular values of the matrix are equal to 0. Okay. Now, what if you do this multiplication? You can do this multiplication, okay, and you end up that A can be written in another nice form, which is A is sigma 1, and then the outer product of UA VA, right? So UA VA Hermitian, plus sigma 2 U2 V2 Hermitian, and so on and so forth, right? So this is an M by N matrix. Again, it's the outer product of a vector in matrix U and the corresponding vector in matrix V. So actually matrix A can also be represented in this nice form. I can basically do a summation, and I sweep through basically the strictly positive singular values, and then I have here the outer products UJ, VJ Hermitian. Sometimes this is a useful way of expressing matrix A. Now, yeah, it's a comment. I mean, so some people sometimes do this mistake. UA generally is not unitary. Right? So UA, and the same applies to VA. So it's a matrix that is M by R, right? And R is less than or equal to M. So the columns of UA are unitary. So we are sure that UA Hermitian UA is equal to I R by R. This is true, and you can do it, and we used it actually. But what about UA Hermitian? No, not necessarily equal to I. Okay, so a unitary matrix by definition is a square. Okay, so U itself is unitary. Okay, and for U, same applies to V. U Hermitian is equal to is equal to U Hermitian U, and this is equal to I M by M. Okay, so don't forget that basically UA, if you have UA Hermitian UA, you are basically computing the inner products of the columns of UA. And then you get identity, but UA Hermitian is not. It is equal to identity if it happens that the rank is equal to M. Okay, so in that special case, basically UA will be a square matrix, and then you can say that it is unitary, and basically you can have this equal to that equal to identity. Okay, so keep this in mind. Okay. Now, so if you have matrix A, what about its Hermitian? Okay, do we need like to restart or redo the proof for the Hermitian? No, because now we have that A is equal to U sigma V Hermitian. Okay, so what is A Hermitian? So we take the Hermitian of this side, so basically V Hermitian is V. Sigma Hermitian, well, sigma Hermitian is sigma transpose, right? Because when you do Hermitian, you basically swap, you make the rows columns, and if you have complex quantities, you basically take their complex conjugate. Well, matrix sigma itself, if you know, remember it, basically it's a matrix in which like you have here sigma 1, sigma 2 up to sigma r, and then zeros. Okay, and those sigmas, the singular values, are basically real valued. Okay, so their conjugate is themselves. Okay, so so the Hermitian of sigma, you can write it as Hermitian. It's also transposed because, again, you know, just to highlight the fact that the sigmas are real valued. And then you have U Hermitian. Okay, U Hermitian. So the singular value decomposition of A Hermitian is this one. So it's a V sigma transpose U Hermitian. So basically, what is the SVD of the Hermitian of a matrix? So basically, the U of A Hermitian is V of A, right? So if you want, like, so what is like, so what, you know, if you deal with A Hermitian as a matrix and you do its U sigma V, basically decomposition. So its U is actually V of A itself, and its V is U of A itself, and basically the singular values, the non-zero singular values are exactly the same. Okay, so you just write it like this. Okay, and for A, remember what we showed is that UA is basically the columns of UA are they constitute an orthonormal basis for the range of A, and the columns of VB are for the null space of A. So writing things down here, again, you don't need to redo things from scratch. Then now what we can say is that VA, the columns of VA, are an orthonormal basis for the range of A Hermitian, and the columns of UB are an orthonormal basis for the null space of A Hermitian. So the four fundamental subspaces of matrix A, so the range and null space of A and A Hermitian, those guys are basically the matrices UA and UB and VA and VB. Okay, Frobenius norm of A. So in this course, actually, there is a chapter on matrix norms. So I assume that you know very well about vector norms, but we will have our chapter on matrix norms. So the Frobenius norm is a matrix norm. It is very easy here to define, and so I'm just using it here. The Frobenius norm of a matrix A, it means that, so it's an M by N matrix, so you basically go I from 1 to M, J from 1 to N, then you take Aij, you take the magnitude of element Aij, you square it, you sum, and you sum over all elements in the matrix, and then you take the square root. So that's the Frobenius norm. Okay? So the Frobenius norm squared is basically the sum of the magnitude squares of the elements of matrix A, and this sum of the magnitude square can be written in terms of the trace of A Hermitian A. Okay, so you can basically take matrix A Hermitian A. You can actually write this down explicitly in terms of its elements, and you can show easily that the trace of A Hermitian A is actually the square of the Frobenius norm. Okay, so now the trace of any matrix here A Hermitian A is equal to, so the trace is basically it's the sum of the elements on the main diagonal, but also you can relate it to the eigenvalues. The trace of a matrix is the sum of its eigenvalues. So the trace of A Hermitian A is the sum of the eigenvalues of A Hermitian A. And what are the eigenvalues of A Hermitian A? Those are the squares of the singular values of A. Right, so during the derivation, we started with the eigenvalues of A Hermitian A, and their positive square roots are basically the so-called singular values. And so the trace of A Hermitian A, basically those are the sum of the squares of the singular values. Okay, so we can actually write the Frobenius norm squared of a matrix A as a sum of the squares of the singular values. Okay, so the Frobenius norm squared. So now we have like nice formulas. So it can be written as a trace of A Hermitian A, and now you can also write it as the sum of the squares of the singular values. Okay, and so if you take the Frobenius norm itself, it will be the square root of this sum of squares. And definitely, I mean, because sigma 1 is the biggest guy, this quantity is greater than or equal to sigma 1. So sigma 1 is the maximum singular value of the matrix A. And so the Frobenius norm is always greater than or equal to sigma 1. And actually, sigma 1 itself will turn out to be a matrix norm. And so again, this will come, so we do not need like to basically waste some time on it now. It will come. Sigma 1 itself, the maximum singular value of a matrix, can actually be used as a matrix norm, as we will see later. Okay. Here, basically this paragraph is, in practice, you never, ever compute the SVD using the procedure I used in the derivation. In other words, if I give you a matrix, A, and you want like to find its SVD, you do not really go and compute A Hermitian A and then find its eigenvalues, and then the singular values are basically the square roots of those eigenvalues and so on. So what I explained here is conceptual, but is numerically very bad. So if you if you do your computations on a computer with finite precision, and all computers have finite precision, you will get garbage results, especially if the dimension of A is large. Okay. Of course, in a homework problem, if I tell you, obtain the singular values and so on, you basically follow this. You can do what I did in the derivation itself, but I mean, if you want to use the SVD for a more serious purpose than solving a homework problem, you need to basically implement some specialized algorithms that are very well designed to compute the SVD in a stable way, numerically stable way. Okay, so I mean, in this course we will not basically talk about the exact details, but this is just like an important comment. By the way, this comment also applies to the Gram-Schmidt that I did on the previous page. So Gram-Schmidt, as we teach it, basically this algorithm is, you cannot do it, right? If if you see Gram-Schmidt implemented in, like, let's say MATLAB, it's never done as I did it, like you take a vector and then you subtract the other vectors after weighting them by the inner products and so on. It's numerically unstable. Okay, so again, we can do it on paper, but it's not something that you will, use. Okay, so so there are things here that are basically conceptual, and are not meant that, oh, if you want to compute the SVD, then this is the way. Okay. Any questions? Okay. So the SVD can be related to something very useful called the Moore Penrose Pseudo Inverse. Okay. Right. Penrose, I think he won the Nobel Prize in physics this year. Okay, so basically the idea is, again, you want to generalize the idea of the inverse of a matrix, right? So again, inverse is for square matrices, and not every square matrix is invertible. So what if you basically want to generalize this concept? Okay, so the pseudo inverse is a very nice idea. It tells you that you can basically define a pseudo inverse of a matrix. And it should have basically 4 properties. So if your matrix is m by n, its pseudo inverse is n by m. Okay, so if it's m by n, so it's here n by m. Of course, if it's a square matrix of size 5 by 5, then it remains 5 by 5. But of course, for a rectangular matrix, let's say 7 by 5, the pseudo inverse will be 5 by 7. Okay, so what are the 4 properties of a pseudo inverse? Basically, if you take the pseudo inverse and sandwich it between A and A, you should get A. If you take A and sandwich it between the pseudo inverse, you should get the pseudo inverse. It must be the case that the pseudo inverse multiplied by A and A multiplied by the pseudo inverse, those guys must be both Hermitian. Now, if you design a pseudo inverse that basically obeys those properties. So here are the nice things. I mean, you may wonder, I mean, why these properties? These properties are very nice. First, they ensure that the pseudo inverse of a matrix is unique. Okay, so the pseudo inverse becomes unique once you say, I want my pseudo inverse to obey 1, 2, 3, 4. Then it becomes unique. And basically, the notes on Blackboard, it has the proof for uniqueness. Okay, I will not do it here, but if you are interested, you can read the proof why the pseudo inverse actually defined to obey those 4 conditions will be unique. Okay. Moreover, if your matrix is a square and invertible, then the pseudo inverse becomes the conventional inverse of the matrix. Okay, so again, defining the pseudo inverse in this way, it will ensure that the pseudo inverse is a unique matrix. For every matrix A, there corresponds one pseudo inverse. And basically, if A happens to be a square matrix that is invertible, and if you go and compute the pseudo inverse, it's exactly the inverse of matrix A. But here is more good news. Actually, this unique pseudo inverse can be expressed in terms of the SVD. Okay, so here is the story. Okay, you can show that basically, so let's recall what is a matrix A itself. So matrix A is U sigma V Hermitian, or if you use the reduced SVD, it's UAS VA Hermitian. Okay, so you can show that if you define a matrix as such, so you take V, and then the pseudo inverse of this matrix, which I will explain shortly, and then U Hermitian. Okay, so you take V and U Hermitian. And what is this matrix? You go to matrix sigma, big sigma, and you transpose it. Okay, and basically for the strictly positive elements in matrix sigma, you replace each element by its reciprocal. Okay, so sigma itself, suppose that sigma itself looks like this, sigma 1, sigma 2. Suppose that this is sigma. Okay, then it's pseudo inverse. So again, you transpose the matrix. So this is not the, so this is one step, you transpose the matrix, sigma to 0, and then for the non-zero components, which are basically the strictly positive singular values, you take the reciprocal. Okay, so this will be this guy here. Okay, so you can take you can basically obtain the pseudo inverse of matrix A by basically doing this. Take V, the V matrix of A itself, the U matrix of A itself, and the sigma matrix of A itself, and then play this game. So you take V multiplied by the pseudo inverse of big sigma multiplied by U Hermitian, and in the reduced form will be VA S inverse UA Hermitian. How can you actually you show that actually this is the pseudo inverse? I mean, who say that this is the pseudo inverse? Easy. Take this quantity here as a pseudo inverse and check that it basically satisfies these 4 things. And I think that also there is a part in the notes in which I did this explicitly. Okay, so how do we know that it's the pseudo inverse? We know that it's the pseudo inverse. You know, basically go and multiply a dagger a dagger a dagger and so on, and you will find that it basically satisfies those 4 quantities. And because the pseudo inverse is unique, then it's the pseudo inverse. Okay, so this is the pseudo. So you can basically use the SVD to obtain the pseudo inverse of the matrix. And here is basically the point that I mentioned. It's very important that if your matrix happens to be square and invertible, its pseudo inverse is the conventional inverse that you know. Okay. Now, so now the SVD is related to pseudo inverse. So the pseudo inverse is a general concept. And you know, just before I proceed, now if you have a problem regarding pseudo inverses, then you can to handle the problem, you can use actually the SVD representation of the pseudo inverse, or you can directly use the properties of the pseudo inverse. Sometimes using those properties is more basically convenient. Sometimes using this guy is more convenient. Okay, so you keep them in mind. So if you start using the SVD and things get stuck, perhaps you just need to basically make use of the properties of the pseudo inverse. Okay, so least squares, basically SVD is related to pseudo inverse, and they are both related to the problem of least squares, which is a very important problem in data science. And in, you know, whenever you do like fitting or modeling and so on, basically you somehow do least squares. So suppose that you have a matrix A and a vector B, and we are interested in basically in obtaining vector X such that the L2 norm of AX minus B is minimized. Okay, so our problem is like this. So it's an optimization problem, minimize. So here is our optimization variables are basically the elements or components of vector X, and we want to minimize. A is a known matrix. I want to find X such that when A is multiplied by X, and then we compute the difference between this vector and vector B, which is a known vector, we want this L2 norm to be minimized. Okay, so that's the least square problem. Now, it happens that the solution is, so what is the solution? What is X that basically minimizes? So the minimizer, as we will see, the minimizer is nothing but the pseudo inverse of A multiplied by B. So the minimizer is the pseudo inverse multiplied by B. Okay, for any general, and so here I'm assuming that A is any general matrix, and because the pseudo inverse is basically is you can write it down in terms of the SVD, and the SVD is for any general matrix. I don't need like to make assumptions regarding the columns of A, that they are linearly independent or anything, or that A is a square or skinny or something like this. I can do this for any general matrix. Okay, how can we prove something like this? Okay, so take the L2 norm squared of AX minus B. Okay, defines it to be the pseudo inverse of A multiplied by B, and then add and subtract Z. So here we have AZ minus B, so it's AZ minus B, and then A of X minus Z. Now this is the L2 norm squared of two vectors, so this is one of them, AZ minus B, and the other one is AX minus Z. So basically the L2 norm squared will be the L2 norm squared of the first vector, the L2 norm squared of the second vector, and the cross terms, which will be basically the inner products. So this will be X minus Z Hermitian, A Hermitian, AZ minus B, and basically it's Hermitian. Okay, so again, this means that this quantity here is exactly equal to this quantity here. So what is the difference? Here we have a general vector X. Here we have X replaced by Z, and that is the pseudo inverse of A multiplied by B. And here we have this vector, and then we have those cross terms. So let's now show that basically the cross terms are 0. So let's focus here. A Hermitian AZ minus B. What is Z? So Z is equal by definition. It's the pseudo inverse of A multiplied by B, like this. Okay, and you can take B as a common factor and put it on the right. Now, from the definition of the pseudo inverse, basically this is exactly equal to its Hermitian. This is one of the requirements of the pseudo inverse, so I can write it as A dagger Hermitian. Okay, and then basically these two Hermitian can be combined as A dagger A Hermitian, right? So basically if you take the Hermitian of this guy, you will get this one. Now again, from the properties of the pseudo inverse, if you take the pseudo inverse and sandwich it between two copies of A, you get the pseudo inverse, right? Sorry, you get A. So basically those guys will give you A, and so you have Hermitian. So it's A Hermitian minus A Hermitian, and that's 0. So basically this term here, and the other side you find its Hermitian, is exactly equal to 0. Okay. So so now we have basically this nice equality. So if you take a general vector x, the L2 norm squared of ax minus b is equal to the L2 norm squared of az minus b, where z is this guy, plus the L2 norm squared of a multiplied by the difference between x and z. Now this is an L2 norm squared, so it's a non-negative quantity. So if this guy is equal to this guy plus a non-negative quantity, then it means that this guy is strictly, that this guy is greater than or equal to basically this guy, right? So you have, again, you have this is exactly equal to the sum, and since this quantity is non-negative, then we have that for a general x, ax minus b, L2 norm squared is greater than or equal to az minus b. Okay, and so this shows what? That the minimizer of ax, the L2 norm squared, or the L2 norm of ax minus b, is z, and that is the pseudo inverse multiplied by b. Okay, so that's the minimizer. So that's the solution to the least squares problem. Now, can we have equality? So can we have equality? So you have equality if this term here is strictly equal to 0. And if a vector norm is equal to 0, it must be the case that the vector itself is equal to 0. So we have equality if and only if basically this is the all 0 vector. Okay, so for any vector x that satisfies this, then basically the vector x will also be a minimizer, right? So here a multiplied by x minus z is the all 0 vector. So if you see this equation, it automatically tells you this minus z is in null of a, right? The null space of a. And so basically any solution, so basically the solution to the least square problem is z plus any vector in the null space of A. So that's the general solution. So the general solution to the least squares problem is the pseudo inverse B, and then you can add any vector living in the null space of A. So you have a unique solution to the least squares problem if the null space of matrix A is only the all 0 vector. It's the trivial null space. If A has a non-trivial null space, then actually there are infinite solutions to the least squares problem. Again, you can get those solutions by taking the pseudo inverse of A multiplied by B and then add any vector from the null space of A. Any questions? Okay, one very useful inequality is the Neumann trace inequality, and it's an inequality that basically is related to the magnitude of the trace of a product of two matrices, and it has an upper bound on that magnitude in terms of the singular values. Basically, the proof, I have an elementary proof for the Neumann trace inequality in the notes. It's very nice. You are advised actually to read it, but I mean, again, it depends on your time and other commitments. Okay, so the proof is in the notes. It's a very cool inequality, and basically it tells you that so you have the trace of AB, and one guy is m by n, the other guy is n by m, you are interested in upper bounding the magnitude of the trace. And so basically what you can upper bound with is that you have a summation, okay, and then you can take k from 1 to the minimum of rank A, rank B, okay, so the sum extends to the minimum of the two ranks of sigma AK, sigma BK. Okay, so basically this summation is the maximum singular value of A multiplied by the maximum singular value of B plus the second maximum plus the third maximum, okay, of B, and so on. And you stop whenever you hit the minimum rank, because we know that basically a singular value with an index that is higher than the rank is exactly equal to 0. Okay, so it's a very useful inequality, and you know, keep it in mind, you know, whenever like you have like a problem in which like you need to have a bound on the trace, on the magnitude of the trace. Okay, so actually we'll use it now. Suppose that you have two matrices, C and D, and C and D are of the same size. So you compute their difference, and you take the Frobenius norm of the difference squared. So so claim basically you can lower bound the square of the Frobenius distance. Sorry, the square of the Frobenius norm of the distance between C and D, or the C minus D, using basically also the singular values of C and of D. Okay, so here what you can do is that you say that I have C minus D, the difference or distance between C and D, you compute the Frobenius norm squared. This is always lower bounded by, and then a summation, and then you take the singular values of C and singular values of D, take the difference, and then you square, and basically you have a sum, and this sum now it goes to the maximum rank. Why is this true? Okay, and this lower bound actually is very useful. So here's basically quickly the idea. So the Frobenius norm squared is the trace of the matrix multiplied by the Hermitian of the matrix. Okay, so again, the original proof of the Frobenius norm is that it is the square root of the sum of the magnitude squares of the elements of the matrix, and the square of the Frobenius norm again can be nicely expressed in terms of the trace of the matrix multiplied by its Hermitian. So trace C minus D, C Hermitian minus D Hermitian, and then you multiply, so you get 4 terms. So basically you get trace C Hermitian, that's the square of the Frobenius norm of C. You get DD Hermitian, trace DD Hermitian, so that's the square of the Frobenius norm of D, and then you get cross terms. You get minus trace CD Hermitian minus trace DC Hermitian. Okay? Now, basically, the trace here is thus the magnitude of the trace of CD Hermitian plus the trace of DC Hermitian. Okay, you can show basically that one of them is the complex conjugate of the other, and if you have complex numbers, so basically if you have Z plus Z conjugate, okay, so Z here is a complex number. If you add two complex conjugate numbers, so basically you get what? You get double the real part, right? And it's always the case for a complex number that the magnitude of the real part is less than or equal to the magnitude of the complex number itself. The magnitude of the complex number itself, right? Again, this is because the magnitude of the complex number is basically the square root of the real part squared plus the imaginary part squared, and so the magnitude of the real part is always less than or equal to the magnitude. Okay, so basically this magnitude is upper bounded by 2. The magnitude of of one of the guys here, trace CD Hermitian. Okay, and now you find the trace, and you find the product of two matrices, and you find magnitude. So something should like alarm you that basically perhaps this is a place where you can apply the Neumann trace basically inequality. It's exactly this. It's an upper bound on the magnitude of the trace of the product of two matrices. So here our two matrices are C and D Hermitian, and we are interested in an upper bound on the magnitude. And so according to the Neumann trace inequality, basically this magnitude is upper bounded by a sum, and in this sum you basically have the singular values of C and D. The corresponding singular values are multiplied together, and then starting from the maximum guys going down, then you sum. Okay, so basically the magnitude of the sum by the Neumann trace inequality is less than or equal to, it's upper bounded by, basically this quantity. Okay, so so if we go back here, so again so we don't lose track. So C minus D, Frobenius norm squared. So it is equal to this Frobenius norm squared plus this Frobenius norm squared minus the sum of the trace plus the trace. Okay, and this is always greater than or equal to the Frobenius norm, and you can always, if you have minus sum, the sum of two numbers, basically, if you have minus a quantity, this is always greater than or equal to if you have a minus, and then you put a magnitude, right? The trace, magnitude of the trace. Okay. And then we have an upper bound on this magnitude. Okay, so this magnitude, we have an upper bound, and if you multiply both sides by -1, then this inequality is reversed and we get a lower bound, right? So let's put it in another color. If this is less than or equal to that, then it means that minus trace CD Hermitian plus trace DC Hermitian, this is greater than or equal to -2 the sum L from 1 to R, sigma CL, sigma DL. Okay, so we have a lower bound now. So, so basically, Neumann trace inequality gave us an upper bound on this magnitude, but this magnitude appears with a minus sign in this basic expansion of the square of the Frobenius norm of C minus D. And so now we have a lower bound. And remember that we said that basically the Frobenius norm square of a matrix, it can be written as the sum of the squares of the singular values. So you can take basically these two quantities here and write down things in terms of the squares of the singular values, and then you can combine the three sums as this lower bound. So it's a very important lower bound, and the derivation here basically rests largely on the application of the Neumann trace inequality. Any questions? So why actually we are interested in this like lower bounding business? Okay, so a very important problem, very important linear algebra, data analysis, and in many fields, signal processing, and so on, is suppose that I give you a matrix X of size MP. So this is my matrix. It has some rank R. Suppose that I want to find a matrix Y of the same size as X, so it's M by M. But I want the so-called low rank approximation. So if this rank X is R, I want matrix Y to have a rank that is K, where the rank of Y is strictly less than the rank of matrix X. So, for a given matrix X, it is required that we obtain another matrix of the same size, but with a strictly smaller rank. And to do what? To obey what? What is the criterion here? We want the difference between these two matrices. If you compute the Frobenius norm, or the Frobenius norm squared of the difference. You can square it. We want basically this quantity to be minimized. Okay, so let's write down our optimization problem. So minimize over y. Y is not any arbitrary matrix. It's the same dimensions as x. Moreover, rank y is equal to k strictly less than r, such that this difference is minimized. So what is the solution to this optimization problem? Okay. So I will tell you the solution first. So it turns out that the solution is SVD. What you do is that you do the SVD of x. Okay, so you do the SVD of x. Okay, and so you take basically v sigma u Hermitian, or VA. It's u sigma v Hermitian, or UAS VA Hermitian, right? And so basically matrix Y is the same as matrix X. What you do is that, so Y is, you take UA, you take VA Hermitian like this. What you do is that in the middle, you put basically the largest k singular values of matrix X, so sigma 1, sigma 2 up to sigma k, and then zeros. So it turns out that the solution to this optimization problem is simply the following. Do the singular value decomposition of matrix X, and what you do is that basically you replace the singular values of X by basically you keep the k largest singular values, and for the singular values from sigma k plus 1 to sigma r, so for matrix X those guys are strictly positive, but in matrix Y, because you want the rank of matrix Y to be k, you simply set everything, those guys to 0. So this is one very, you can say it's the most important application of SVD. Like again, you want to approximate a matrix. You have a matrix X with a certain rank. You want to approximate it with a lower rank matrix, okay, and such that the difference between the two matrices, if you compute the Frobenius norm of the difference, it's minimized. So the solution is SVD, and keep the largest k singular values. Okay, how can we choose something like this quickly? Basically, yes, k is given. Yes, exactly. So you say I want basically rank 2 matrix, rank 1, or rank anything that is smaller than R. K is given here. Okay, so how can we show that this is actually true? I will skim quickly through the derivation. So basically, you apply the inequality from the previous slide. So we have a lower bound on the square of the Frobenius norm of x minus y. Okay, so this can be given by this summation here, which involves the difference between the singular values. Now, you take this summation here and you split it into two parts. So a summation from 1 to k, and then another part that basically the index goes from k plus 1 to rank of x. Remember, rank of x is r, and basically k is strictly less than r. And basically, because we want matrix Y to have a rank of k, then the number of strictly positive singular values of Y should be k. So the singular values of Y above k are all equal to 0. Okay, so here we will have, it's like I wrote here sigma x squared. It is sigma x L minus sigma y L squared, but because the index L here is k plus 1 up to rank of x, and the rank of matrix Y is k, then basically this is 0, and then we have basically this quantity. Okay, so this is the basically a lower bound on this Frobenius norm. Okay. So how can we make this thing minimum? How can we minimize it? What do we control? We control matrix Y. Matrix Y basically is like the optimization variable in a matrix form. This is what we control and we design. So to minimize this lower bound, what we can do is that corresponding to the k largest singular values of x, we basically choose the k positive singular values of y to be exactly the same as the k largest singular values of x. In other words, to minimize this lower bound, what you can do is that you choose sigma y1 to be exactly equal to sigma x1, sigma y2 equal to sigma x2, and so on. And by doing this choice, basically this quantity here will be crushed to 0. What about this quantity? This quantity you cannot control, because this is a summation, and this summation is over the singular values of x, which is a given matrix with some given singular values. So you cannot control this one, and because matrix Y has only k strictly positive singular values, then again what the best you can do to minimize the lower bound is to choose to do this. Sigma y1 is sigma x1, sigma y2 is sigma x2, and so on and so forth, so that this is equal to 0, and basically this will be the residual. It will be the lower bound. Now you may say, well, I mean, but I mean, so you have a lower bound on a quantity, but who says that actually you can make this Frobenius norm squared exactly equal to the lower bound? Right? So if you want to minimize a function, right? So suppose that you have a function f of x, and you want to of f of alpha, and you want to minimize it, and then you somehow showed that f of alpha is greater than or equal to 7. So 7 is a lower bound. Does this mean that basically the minimum of the function is equal to 7? No. So you can have a function that looks like this, and it's well above. So 7 is indeed a lower bound, but it's not achievable, and the minimum of the function is strictly higher than the lower bound. So by having a lower bound on the square of the Frobenius norm, this is not enough to make the claim that actually, you know, this basically assignment of values is our solution. To show that this is a solution, we need to show that the lower bound is achievable, which means that we need to show that there is a y that can be chosen, a full Y matrix, not just we select its singular values, we also select its right and left singular vectors, and we show that actually this will allow us to achieve the lower bound. Okay? So it turns out that it's easy, as I said here at the beginning. You know, take Y, and for Y, you know, you can basically, I will leave the argument for you to read, but basically the idea is that you take Y, its singular values will be, so this is matrix Y, you take the first k singular values, and the remaining are zeros, and you simply take the u vectors corresponding here, the ku vectors corresponding to those k singular singular values, and here v1 Hermitian vk. Okay, so basically Y is a copy of X. It's just that you set the singular values from k plus 1 to r, you set them equal to 0. And again, you can easily show, as you see in this argument, that this will achieve the lower bound, which is this summation here. Okay, so the last thing I will say is, so this is the theorem, that we have a matrix X, and we are interested in minimizing the Frobenius norm, or the Frobenius norm squared, between X, of the difference between X and Y, under the constraint, so it's not just a minimization. You know, if it's just an unconstrained minimization, you set y equal to x and you get the Frobenius norm equal to 0. No, we have a constraint. The constraint is that the rank of y should be k, and k is strictly less than the rank of x, which is r. Now, the minimum of this quantity is basically this summation here, which is this term here. Okay, is this really the minimizer? Yes. You know, is this really the minimum value of the Frobenius norm? Yes, and the way of doing it is simply this. Okay, so if this is the SVD of x, SVD of r you copy. Okay, so you take those guys, you take k of them, you take those guys, you take k of them, and then you take the k largest singular values of matrix X. Okay, so so this will be the solution.